Lift and drag are always connected, and perhaps never more so than when a plane enters stall. On a cold winter day in 2009 in upstate New York, Captain Marvin Renslow and First Officer Rebecca Shaw were at the controls of a Bombardier Dash 8 Q400 operated by Colgan Air. The flight was a short 52-minute hop from Newark, New Jersey to Buffalo, New York. Unfortunately, the flight would never arrive at its intended destination. As the aircraft approached the Buffalo airport, the weather conditions there were a wintry mix of light snow, fog, moderate winds, and a temperature of 1 degree Celsius. The captain and first officer noted ice accumulation on the wings and windshield as they approached the vicinity of the airport. After lining up with the final approach course and lowering the landing gear and the flaps, the aircraft's speed began to decay more than normal. As the autopilot worked to hold the aircraft's altitude, suddenly the wing lost a lot of lift and the aircraft began to fall out of control. Only about 20 seconds after the first sign of trouble, the flight crashed nose first into the ground and the aircraft exploded into flames. Sadly, this incident resulted in the death of all 49 passengers and crew, along with one person on the ground. Let's talk about what happened and how a routine flight could go so horribly wrong in just a moment. The fundamental aerodynamic principle at work relates to how lift and drag work together on a wing to govern the properties of flight. Since the amount of lift generated by a wing is directly related to its angle of attack relative to the oncoming flow, higher angles give more lift. If the wing needs to generate a higher lift coefficient, for example to fly more slowly, then the aircraft can be pitched up to a higher angle of attack. This is because the lift must remain equal to the weight, and as the airspeed goes down, the lift coefficient must go up. The primary way that a pilot can increase lift coefficient is by increasing the angle of attack of the wing as the nose is pitched up. This increases the amount of flow turning and increases the downward deflection of the wake downstream of the wing. And from Newton's third law, the lift increases. In the Colgan Air 3407 crash, accumulation of ice on the wings and windshield increased the aerodynamic drag. The presence of the ice disrupted the smooth flow of air over the wings, and the roughness of the ice led to much higher viscous drag. Also, the ice would likely lead to small pockets of separated flow, which would significantly increase the pressure drag. The overall impact of this ice accumulation is more sluggish aerodynamic performance that should be counteracted by increasing the throttle setting on the engines. Since the pilots did not add power to overcome this additional drag, the aircraft began to decelerate. The autopilot, which controls the aircraft's altitude, its pitch, roll, and yaw orientation, continued to pitch the aircraft to higher angle of attack in order to generate enough lift to maintain constant altitude. There is a limit, however, to how much lift can be generated by a wing, or how high the angle of attack can go before significant problems are encountered. Beyond a certain critical angle of attack, the flow streamlines cannot successfully negotiate the aggressive curvature near the leading edge of the wing, and the streamlines depart from the wing's curvature. In other words, the flow separates. This flow separation event occurs because the boundary layer has insufficient momentum to counteract the adverse pressure gradient that the flow is working against. The stronger the curvature of the flow streamlines, the more intense the changes in pressure will be, and the harder it will be for the flow momentum to overcome the increase in pressure required to recover back up to high pressure at the trailing edge. And the most significant consequences of flow separation over a wing is a dramatic loss of lift, which is called stall. The onset of this flow separation can happen very quickly as the wing is pitched to higher angles. It's a very grave situation in an aircraft, since the aircraft will begin to fall when lift is lost during a stall. Each aircraft has specific stall characteristics. There is a physical angle of attack and corresponding minimum speed at which it can fly. Any lower flight speed will result in a stall. This is precisely what happened in the case of the Colgan Air crash. The insidious thing about ice accumulation on the wings is that it changes the stall characteristics of the airplane, often in unpredictable ways that the pilot may not recognize. When ice accumulates on the wing, it changes the shape of the wing, adding increased roughness and curvature, making it much more prone to flow separation. Thus, the flight speed at which an aircraft will stall can dramatically increase in icing conditions. Let's look at ice on the leading edge of a wing. There is a resulting flow field around it. Clearly, the airflow is disturbed significantly and the wing is no longer aerodynamically clean. The problem, though, is that the accumulation of ice is extremely difficult to predict. The exact shapes that result from various conditions are a result of the complex interaction between three-dimensional aerodynamics, heat transfer, and the size, temperature, phase, and density of water droplets that interact with the wing. This is actually an active area of research to understand and reliably predict how ice accumulates and inform strategies for mitigating the problem. For the Colgan air crash, the Dash 8 aircraft would normally be flown at an approach speed of 145 knots with no flaps in order to be well away from the stall speed of 118 knots for a clean wing. However, in icing conditions, the limiting stall angle of attack decreases and the stall speed goes up by an unknown amount due to the uncertainty of ice accretion. Thus, safe operating procedures in icing conditions require that the approach speed be set 25 knots higher than normal at 170 knots in order to add a margin of safety. So if a pilot encounters unexpected stall condition, what can be done? Is all hope lost? Thankfully, it is a recoverable situation as long as there is sufficient altitude and the pilot responds quickly and accurately. In order to recover from a stall, the pilot must actually point the nose down in order to decrease the angle of attack and re-establish flow over the wing that follows the curvature of the airfoil. Wait a minute, this seems counterintuitive. The pilots must actually push the nose down while descending in order to recover from a stall. This procedure is the exact opposite of our gut instinct, which would lead us to pull up to somehow arrest the descent. The problem with pulling up in an attempt to arrest the descent is that it actually makes the stall worse. Pulling up to increase lift only works when you have smooth attached airflow over the wings. But pulling up in a stall only exacerbates the stall, leading to even greater loss of lift. Take a look at this plot of the lift coefficient as a function of angle of attack. The stall is indicated by the inflection point in the curve. Before stall, the pilot can easily increase angle of attack in order to increase the lift. However, the limit to this trend is stall. And beyond stall, the exact opposite trend occurs. Further increases in the angle of attack result in lower lift. Sadly, this is exactly the mistake that the captain of the Colgan Air flight made. He pulled back on the control yoke, pitching the aircraft up as high as 19 degrees angle of attack, which is well beyond what any commercial airliner can handle. This high angle of attack made his stall condition even worse, leading to asymmetric lift on the wings, causing the aircraft to lose directional control and spin into the ground. The proper procedure for the pilots would be to push the nose down and throttle the engines to maximum speed. This condition would be held momentarily until a lower angle of attack and higher flight speed is established, which allows the wings to recover their benign lift-producing characteristics. Only after lift has been restored can the pilot pull out of the descent and recover to the original flight altitude. Now you may be wondering about what can be done to prevent such a horrific situation as the Colgan air crash. Wintry weather is a routine occurrence in many places throughout the world. Why don't we see more airplane crashes due to icing conditions? Well, there are a number of aircraft design aspects and operational procedures that counteract the icing problem. Aircraft that routinely fly in icing conditions must be certified with systems that can effectively remove ice from the wings. There are several strategies for doing this. Many larger jet aircraft use warm air that is bled off the compressors of the jet engines to circulate through ducting right behind the leading edge of the wing. The hot air heats the leading edge, melting any ice that is accumulated and preventing further ice accumulation in most situations. Another strategy is what is called a weeping wing, where a large number of small holes are manufactured in the leading edge of the wing and an antifreeze fluid is pumped through the holes and used to melt the ice. A third strategy is to use inflatable rubber boots on the leading edge of the wing. These rubber sleeves have air pumped into them and they inflate just like a balloon would. The expansion of the boots causes the ice to mechanically break up and shed off the surface. Each of these concepts must be tested extensively for robustness and certified for aircraft to be able to fly into known icing conditions, what we call FICI certification. These de-icing and anti-ice systems are effective at removing ice in flight when there is air flowing over the wings to carry the ice away. But what must be done when an aircraft is covered in snow and ice before it pushes back from the gate? This leads to the required de-icing that routinely occurs at airports in wintry conditions. If there is any visible ice or snow accumulation on the aircraft, it must be de-iced before taxiing for takeoff. Aircraft taxi over to the de-icing pad, where trucks surround the aircraft and spray a de-icing formulation over the wings, engines, and fuselage. This fluid serves to remove any ice on the aircraft and also has an anti-ice component that helps prevent further ice accumulation while the aircraft is on the ground under wintry precipitation. Let's now return our attention to the aerodynamics of lift and drag and how they interact on a wing. The previous discussion for controlling lift by changing the angle of attack is true for a given airfoil and wing geometry. Essentially, this is a pilot's perspective on how lift can be controlled. But let's take a step back and consider what an aircraft designer might be able to do to control the lift produced by an airfoil or wing. Given that the lift is directly related to the turning of the flow streamlines, we might be able to achieve greater flow turning for an airfoil at a given angle by changing the curvature of the airfoil. The amount of curvature is referred to as the airfoil camber. A highly cambered airfoil with convex curvature, of course, will generate significant lift even at zero angle of attack. In contrast, a completely symmetric airfoil with exactly the same curvature above and below the midline then will produce no lift when it is at zero angle of attack, since there is no net downward deflection of the flow behind the airfoil. However, if a symmetric airfoil is oriented at an angle with respect to the flow, then it will produce lift. Since positive and negative angles of attack present the same situation to the oncoming airflow, a symmetric airfoil can just as easily fly in inverted flight. For this reason, symmetric airfoils are very useful on aerobatic aircraft, which spend a significant amount of time in inverted flight. The airfoil has the same aerodynamic characteristics whether the plane is right side up or upside down. Now, what if we want to somehow increase the lift coefficient beyond what the airfoil is naturally capable of doing? What if we could shift the stall angle of attack to a higher angle? If we could do this, we could fly the aircraft much more slowly. And if we can fly the aircraft more slowly, we can dramatically decrease the runway length required to bring the aircraft to a stop. Just look at this example of a bush pilot in Alaska who is in very slow flight and somehow managing to land the aircraft within an incredibly short distance. This enables the pilot to drop the aircraft into very tight, remote landing areas in order to deliver food, fuel, and other necessities in even the remotest corners of Alaska. For this reason, the aircraft is like the pickup truck for Alaskans. It connects remote villages to civilization in ways that are otherwise impossible. The aerodynamic trick that this pilot employs is to actually change the shape of the airfoil in flight. On this aircraft, the pilot has deployed a flap, which changes the shape of the airfoil to enhance flow turning, resulting in a greater downward deflection of the flow streamlines. Other devices, known as slats, can be extended from the leading edge of the airfoil to achieve the same purpose. And this is not such an esoteric approach. Commercial airliners also use slats and flaps to actively change the shape of the wing on final approach to landing. By changing the shape of the wing, the aircraft is allowing the pilots to fly the airplane with a higher lift coefficient and enabling a lower flight speed while still maintaining lift equal to weight. The designer's challenge, then, is to create a functional flap and slat system that will reliably extend and retract under all circumstances, will retract into an aerodynamically clean configuration for efficient cruise, and at the same time will provide high lift at low speeds. Let's look at the aerodynamics of flaps and slats in a little more detail. There are several different kinds of flaps that can be used. One of the simplest methods is to install a hinge in a segment of the wing, somewhere near the trailing edge, to allow the pilot to drop the last portion of the wing down at an angle. This flap design is most commonly found on small general aviation aircraft due to its relative simplicity and low cost. The aerodynamic function of the flap is to simply increase the camber of the wing, but in a way that can be changed in flight. This allows for a wing configuration that is optimized for cruise, which is when only a moderate lift coefficient is needed due to the high flight speed, while meeting the need for low drag. At the same time, the use of a flap allows for the airplane to fly much more slowly than it normally can with its cruise-optimized wing. In this plot of the lift coefficient, we can see that the lift coefficient for a given angle of attack is increased dramatically when the flap is deployed, and that higher lift coefficient will allow a pilot to fly more slowly. Now let's take a look at the other end of the spectrum of system complexity. A commercial airliner such as the Boeing 747 has a very complex high-lift system that allows it to have an approach speed as low as about 160 miles per hour, but still cruise at a top speed of over 600 miles per hour. The 747 has a series of both flaps and slats which work together to dramatically increase the camber of the wing. The slat is a strongly curved airfoil that deploys from the leading edge. At the trailing edge of the 747's wing, a whole series of flaps deploys, not just one. Each flap is set at a successively higher angle, allowing the flow to do a better job of negotiating the strong curvature without separating. This flap and slat system produces an amazing amount of flow curvature without separating. Now, you may be wondering why aircraft designers don't simply design the wing with these great flaps permanently deployed. The reason is drag. These high lift configurations not only produce a lot of lift, but they also have a lot of drag. Extra drag really isn't a problem when the pilot is trying to slow down on the aircraft on final approach, but extra drag is a problem in cruise flight. By the way, when I mentioned that the 747 has an approach speed as low as about 160 miles per hour, that still seems pretty high, right? That's 2.5 times the speed that we normally drive down the highway. Yet the pilot is able to successfully steer the aircraft to maintain the center line of the runway and bring the aircraft to a stop within about a mile. Up until now, we've mostly been thinking of the wing's aerodynamics in a two-dimensional sense. But a quick look at the wing profile reveals that the wing is anything but 2D. Across the span of the wing, there is a substantial variation in the distance from the leading to trailing edge, which is termed the wing chord. There are several reasons for this taper of the wing, and one of which relates to the three-dimensional stall characteristics of this wing. And here is the key point when it comes to the three-dimensional nature of wing stall. It is really important for the wing to stall at the root rather than at the tip. Why? Because the aircraft has control surfaces called ailerons that are located near the wing tips, and it is critical to maintain attached flow over the ailerons in order to maintain roll control. If the flow were to separate at the wing tips first, the ailerons would lose effectiveness in the slow, unsteady separated flow, making it much more difficult for the pilot to maintain control of the aircraft during a stall event. Unfortunately, some of the natural aerodynamic characteristics of swept-back wings that we see on most commercial airliners will naturally lead to stall at the wing tip first. But aircraft designers have a few tricks up their sleeves to make sure that stall happens inboard first.